officially is recording. We have small delay, but that should be fine with the short break located after the session. And the next speaker is Jan Kavan, and he's actually also presenting from Iceland, but not exactly from our location. And he's both now representing Iceland and Czech Republic. So Jan, the floor is yours.
Okay, hello everybody. Thanks Pavla for introduction. As you already told, I'm in Iceland, but I will speak about Antarctica, so the whole workshop will be kind of a global. At least I think I'm the only one from the Southern Hemisphere. Anyway, I will try to share the screen. And just please let me know if you can see the presentation.
Yes.
Okay, great. So as I already told you, I will show you an example from Antarctica, from James Ross Island, where there is a Czech Antarctic station. And I will focus on, let's say, controls of topography or atmospheric conditions on the high latitude dust deposition and all these like aeolian processes. The site is located on the tip of the Antarctic Peninsula, on its eastern side, which is quite nice because we are in kind of like a rain shadow. So the precipitations are really low, around like 200 millimeters per year. And this results in quite a dry area. So we have this area on the satellite image on the right, which is Ulu Peninsula, the northernmost part of the James Ross Island. It's about 300 square kilometers of ice-free area, like pure dry land. The Czech station is on the northern shore here, and this also results in the presence of like really like big dust storms, which is not very nice for people working there. But if you study dust, then it's perfect. So we try to take advantage of this, let's say, not very pleasant feature, but it's one of the like nicest records of dust storms from the Antarctica. So I will just show you like let's say brief overview of few studies that we did in the past like 5 years, also with other colleagues as Pavla and others. So the very first thing is to just look how the wind conditions look like and how it is affected by the topography. So here on the map on the right, we mapped like the prevailing wind patterns over the peninsula, and we compare it also with the instrumental observations. So we have some wind, speed, and direction weather stations all around the area. And as you see on the windrows on the left, which is the uppermost one on top of the ice dome, so the prevailing wind is from the south, but then it is somehow modified by the topography. So these like small gray arrows shows the local direction of the wind. So it's mostly from the south, but then it's modified by the local topography, by the terrain, which is quite nice. And what's also very interesting from the chemical composition point of view is that the local like bedrock geology is very complex. We have a combination of volcanic rocks, which are all these like orange and violet colors in the map. And this is combined with mostly Cretaceous sedimentary rocks, sandstones mostly, which are here depicted in the green tones, and then some gray sedimentary rocks as well. So this makes kind of a special mixture of two very different, chemically different rock types, which is then imprinted in the sediment samples. So quite a nice feature for mapping the sources of the sediments. So Antarctica is quite logistically difficult, so we don't really have such a nice, sophisticated instrument as we already saw in some previous presentations. But we try to make the most of of our opportunities. So we basically have these passive samplers that we set up on the profile from the station towards south, and we just collected it opportunistically. When we see there's a dust storm, then we go and collect it and process the samples. We also have this aerosol counter, which was provided by Pavla, in fact, and this is for continuous measurement of the concentrations. So we combine these few different approaches, let's say, and we also have the network of automatic weather stations where we measure wind speed, direction, other parameters such as air temperature, humidity, and so on. Just for this particular image, I put it there because that's exactly how it looks after a dust storm. So you see the direct deposition of the dust on the instrument itself. So then it's pretty easy to collect the samples itself, like a physical sample for some further analysis. And we also looked more in details into the samples itself. So we performed a grain size analysis and X-ray fluorescence analysis for chemical composition. So this is how it looked when we collect the samples after the whole summer season, which is like almost 2 months here. And we see the dust deposition rate, grams per square meter. But what's important to see the spatial pattern. So we see in the southern part, there's quite high deposition in this rather flat area. And then when we go to the more, let's say, topographically variable part of the profile, we see some really huge differences in the deposition rate, like a huge deposition just behind the crest, and then very low deposition here next to the seashore. So this is how it looks on the profile itself. In the dark blue curve, you have the terrain profile, and the light blue depicts the deposition rate. What's interesting is this sample, W24, which I will speak in a few slides after this. This is the grain size median of the sample. So you see the grain size can be pretty high because there's a mixture of let's say long range transport and some local sources just around the sampler itself. So it's difficult to distinguish what is long range transported particle and what is locally transported particle. In 2018, we had 3 major dust storms during the whole measurement period. As you see on the graph on the right-hand side, there's wind speed. So there are the 3 major dust storms or high wind speed events. The problem is, or the interesting thing is that during the first, let's say, storm, there's almost no response in the dust concentrations. On the other hand, the 2 high wind speed events at the end of the summer season, there is quite nice response in terms of concentration. So basically, it's also important, not just the wind speed itself, but also the surface conditions. Because at the beginning of the summer season, the surface is still very wet, saturated from the snowmelt. So the particles cannot be uplifted. So nothing really surprising, but it's nice to have it confirmed. What is quite new and let's say surprising, it's very important interaction between aeolian and fluvial sediment transport mechanisms, because as we proved, the dust deposition is really an important source of material for the further transport in the fluvial systems. As we see here from the remote sensing image, we have 2 major fluvial systems which transport a lot of material from the land to the sea. And here we can see 2 major deltas that are formed on the shore just next to the outlet of the rivers. And this is how it looks in the field. So on your left, it's the south. So from left, the wind is going to the right. And as you see on the left, it's really like a flat surface full of really like fine sediments that are really easy to transport. And then this kind of sediment is then deposited directly in the braid plane of the river, and the river then bring all the material towards the sea and deposit it there in the form of the huge delta. In 2021, we have also like 3 really like big dust storms, and we put like 3 detailed cross profiles across the braid plane just to see how the braid plane interacts and how the dust is deposited within the braid plane. So we see on the right the three dust storms and the deposition rates. Basically, it looks very similar. So the spatial pattern is very much the same. And you can clearly see the effect of the surface humidity. It's in the central part of the profile, where there is directly the braid plane and the streams. There is almost no deposition, because all the material which goes across the braid plane is directly deposited on the wet surface. And this later on creates the source for the fluvial material. When there is a larger flood, it takes all the material that was deposited from the dust storm, and it goes directly to the sea. This is just a depiction of the elevation model. So you see the configuration of the terrain, and then the blue arrow marks the prevailing wind conditions in the braid plane. What we were also interested was the chemical composition of the samples, of the dust samples, and we compare it with the background. So on the left, you see the background composition of the material on the surface, and on the right, you see the chemical composition of the dust sample itself. What's most striking is there's almost or more than 60% of halite, which indicates the sea spray presence in the dust sample. So there is a lot of material going from the sea that is then deposited on the land. So there is big exchange of the material between sea and the land, not just from land to the sea, but then during the some major major storm, there's also the sea spray coming back to the land. And this is how it looks in the braid plane itself. So you see just on the first side from the color that the braid plane is really dark, it means wet, and the slopes around the braid plane are really dry. So this is how the system works. The deposition is on the floor of the braid plane, which is wet, and major rivers are going through the braid plane. So at the back you see the volcanic mesa. So you will also see it's nicely distinguishable just from the color. The reddish color is the volcanic material. Then the, let's say, more gray or brownish color is the Cretaceous sediments. So then we looked directly in the braid plane and see how it works during the summer season. So basically, the upper left image shows the beginning of the season, when there is still quite some snow deposited inside the braid plane in the valley floor. So you see that the most deposition occurs on the edge of the braid plane. Then in the peak summer, during February, in the blue color, you see that the braid plane itself is getting dry. So you have these kind of peaks on the edge of the braid plane itself, which is already dried after the winter. And then we also calculated the material that is probably deposited during a summer season. So simply measuring the difference between the input, in front of the braid plane and behind the braid plane, we think there is probably about 1,200 tons per year of material deposited within the braid plane itself, just the deposition of the dust. And this is just a conceptual image, how we think it works during the year, in the spring and in the summer. And we wanted to also prove how does it really work. So we looked in detail to the fluvial transport itself, and we tried to quantify the sediment sorted and the pathways and what's controlling the transport. So you see again, like the photograph of the break plane of the whole catchment, and you see the major braid plane, which is like really dark brown, and the rest of the braid plane is already getting dry in the peak summer. What was quite interesting is that if we have the classical like relationship between discharge and suspended sediment concentration, after some major dust storms, this relationship was completely like broken and didn't work at all. There was much more material in the fluvial system than would be expected if we just follow the classical, let's say, normal curve of discharge and suspended sediment curve. So it's one of the proof that there must be some like external input of the material to the fluvial systems, and that's the dust deposition. Yep. And all the dust and all the material which is deposited within the braid plane is then transported to the sea and creates these huge deltas, which are, this particular delta is about 600 meters wide and about 300 meters goes into the sea. So it's really like a huge delta from relatively a small catchment. The catchment has less than 10 square kilometers. So it's really like a small catchment, but it was possible to create this really huge delta. And we just need to, let's say, realize that the delta has been forming for, let's say, only a few thousands of years after the deglaciation of the whole Antarctic Peninsula. So it's really like a really fast process, and there must be really like a huge amount of material that is deposited in the catchment and then transported to the sea. So basically, if I would like to sum it up, so we can say that the topography plays really a crucial role in the high latitudes that deposition like a spatial pattern. And it's not only wind speed and direction, but there's also a combination with the soil surface humidity, which is crucial because we need really like a dry surface to uplift the particles. And that's typically the end of the summer season. Then what's quite interesting and relatively new, it's the interaction of the aerial and fluvial transport systems, which is really like essential for the local sediment budget. There are, of course, examples from Greenland, from the braid plains and other things, but it's usually considered that the braid plane is a source for dust emissions. But here we prove that it's also vice versa. The dust is an important input into the fluvial system. And what we can expect in the future with the climate warming, the summer season is like getting longer and longer, which means there will be like a longer period of a dry surface, which will be then really like sensitive to any major storms. So we can expect that the role of the dust emissions and dust transport will be more significant in the future. Also because we are losing snow cover and glaciers, so these ice-free areas are getting larger. So that's all. I hope it was not very chaotic. I'm sorry it was not very polished, but they just closed the kindergarten today, so I'm alone at home with my small daughter. So the design was probably not really perfect.
It was perfect. We have time for a quick question, maybe one in the room and one online. Is there any question here? Okay, so I will proceed to the online questions. I think it was the highest gas. You have measured there, the gas, wind gas.
I think it was around 20 meters per second, but it's averaged by, I think, 5 minutes. So the actual wind speed during some gusts might be about 30, 35.
And second question, because it was quick one, is the dust activity picks up in Patagonia at the end of the same time as you were showing in your Antarctic Peninsula, said by Santiago Gasso. So there might be maybe some mixture of different dusts.
Might be. I think we, in the paper with you, Pavla, we proved that there is a possible dust source in Patagonia as well.
Good.
So, yeah.
Okay, thank you. We have to now proceed to the next speaker. It was really nice to see this active valley also from South Hemisphere. And our next speaker is Rose Herbert. And now we actually will move more to the impacts of the high latitude dust and low latitude dust as well. So the floor is yours, Rose.
Thank you very much. Let me know if you can't hear me or see my screen.
Yes, we do both.
Brilliant. So yeah, I'm from Leeds, and what I'm showing you today is some modeling work we've been doing. So we're looking at linking the low latitude dust sources to the high latitudes, and we're interested in its role in primary ice production. So as their role as ice nucleating particles. And what's a bit different about what we're looking at is we're looking at like long-lived dusts in terms of timescales that are probably longer than we'd normally think of. So we're thinking of weeks to months to seasons. So yeah, so a bit longer than we would normally think. So I'll start in the Arctic, but I'm going to kind of go globally after at the end. So first of all, dust is always present in the Arctic atmosphere. We've got some long-term observations here from sites around the Arctic, just showing the annual cycle of the dust mass concentration at the surface. And we can see there are annual cycles in some of these locations, but we always see dust of varying magnitudes around the Arctic. So I don't think that's going to surprise anyone. And also, not going to surprise anyone, I think we know that there's local sources and non-local sources. This was a modeling study where the authors looked at the dust in the Arctic and looked where it came from. If we look at the profile here on the left, the purple is the Arctic dust, and then other sources, so the low latitude dust sources. And you can see there's contributions from all these different sources. Maybe there's quite a lot of vertical variation in the contribution, but we can see that this dust comes from local and non-local sources. So onto the research question. We know the Arctic atmosphere is dusty. We know that some of the dust is from non-local sources. And in terms of what we're looking at, we know dust is an important ice nucleating particle species and important for mixed phase clouds and climate. So what we want to look at is how do the long-lived dusts influence the availability of IMPs in the Arctic and just the high latitude atmosphere regions. And so when we talk about long-lived, we're sort of thinking more maybe a month or 3 months, but it also might be that this timescale doesn't matter. Maybe it's only the dust that's been emitted a week ago or so that we actually care about. So I said we're using model to do this. We're using a global climate model, the UK Earth system model. This includes UKCA mode that has this detailed aerosol microphysics scheme and a land surface model as well called Joules. In terms of ice nucleating particle species, we're just focusing on mineral dusts here that are relevant for mixed phase clouds, so the immersion mode freezing process. And in terms of how we actually treat this in the model, so UKCA, which has this aerosol microphysics scheme, this gives us detailed aerosol processes for dust in 3 different size modes. So we're covering all the relevant size modes up to supercoarse as well, so these really large particles. And then to actually get the IMP concentration, we take the modeled dust distributions and apply some parameterizations that are dependent on temperature, but also the surface area per particle. And that's going to be important later on. So to actually look at these different timescales, we've sort of come up with these experiments to test this. So what we have is a number of simulations, all run for 6 months. And we start them for each month of the year. And so for each of these 6-month period, we have one simulation where dust emissions globally are just allowed to continue. And then we also have a paired simulation where at the beginning here, so following some spin up, we turn off all the dust emissions globally. And so it means we're not allowed to emit the dust, but anything that's kind of being advected from the lower latitudes, the high latitudes, is allowed to continue, and removal processes, etc. And we end up with this kind of picture here. So if we look at the Arctic, throughout the year, we've got this, this cycle in the dust mass concentration as a mean. And then these dashed lines are showing what happens when we turn off the dust emissions. And if we can basically pick a month, go vertically through those experiments, and that gives us, allows us to kind of give a dust age to that dust mass and also the IMP concentration. So onto the results. So I'm just starting, so this is the Arctic as a mean from 6 to 85 north. It's the month of the year here. And then the y-axis is the contribution to the total dust mass concentration at the model surface, with the different colors showing the different ages. So this pale color here is quite fresh dust that's only really been around for 30 days. And then as we go darker and darker, it's later and later. And we're going up to 180 days. So we're going to quite a few months that this dust has been in the atmosphere. So what can you see? Most of the dust mass is very fresh, or less than 30 days. So it's kind of fallen out of the column quite quickly. In terms of these older dust masses, we have to zoom into these small percentages here to really get anything that's sort of 1 or 2%. So you can see here in August, this is maybe 120 days upwards. That's only about 2%. So most of the dust mass in the Arctic is fresh. But it's a different story when you actually look at the ice nucleating particle concentration. So now we have that same data for the mass, but next to it, we have the contribution to the total IMP concentration in the Arctic. And this is just for dust. So now we can see that in all months of the year, we have this shift so that the IMP contributions are weighted towards these older dusts. So August here, for example, the mass, 90% of the mass of the dust is from very newly emitted dust particles, but actually the IMP concentration that only contributes maybe 30%, and it's these older dust particles that are having a bigger impact. So in terms of actually spatially around the Arctic, these are just different seasons. So it's the contribution of the total IMP concentration from these dusts that are over 60 days old, so a couple of months old. So for winter and spring, you can see smaller percentages, but in the more remote regions, so up towards the pole, we're getting 30 to 40% of the total IMP concentration is from these dusts that are over 60 days old. And you can really see the summer months here standing out. Now this is going up to 80% upwards of the total IMP concentration. So it's really showing that it's in these really remote regions that are the furthest away from the sources, the primary sources that we have in our model, that we're getting this strongest contribution. So why is this happening? It's kind of, in some ways, it's actually quite simple, really. It's the big particles fall out quicker than the small particles. So this is a month since we've turned off those dust emissions, and then just the diameter of the dust particles in the size distribution. And we're just looking at the decay with time. So if we look above kind of 1 micrometer in diameter, we can see this relatively quick decay when we compare it to these smaller particles. So what's happening is we turn off the dust emissions, the large particles fall out, but the smaller particles stay there. And if we think about, so a lot of the mass is in the large particles, but a lot of the number is in these smaller particles. And so that's why we end up having this, this shift towards these older dust contributions for the IMP concentration. So this made us sort of think more about, okay, which part of the dust size distribution is actually contributing towards the IMP in any locations. This is now globally. And we're going to just take the annual mean dust distribution, size distribution at the model surface and convert it into IMP concentration and see which part of the size distributions are contributing towards that, the IMP concentration there. So we've got large particles, smaller, and then even smaller and the smallest. So close to the major dust source regions, we can see that it's these bigger particles that are really controlling the IMP concentration. Whereas when we shift to these smaller size modes, it's these remote regions. So we've got the open oceans, the Arctic, and to some degree the Southern Ocean, that are actually, it's the smaller particles that are providing most of these remote dust IMPs. And is this actually happening? So these are some IMP measurements made during the Mosaic campaign. So they tethered to the ice sheet and floated with it for a year in the Arctic around the pole. And they measured the IMP concentration but in different sizes. So we have large particles in purple and then the smallest particles in red. And although the large particles do contribute to the IMP concentration a lot, sometimes it was these smallest particles that actually produced the highest number of IMPs. And the authors did kind of say they're not sure why this is actually happening. And so I think this actually could be supported by what we're seeing. And perhaps these are very small particles that may be just being completely missed when we're actually measuring the mass of stuff. So just a final slide here to say this isn't just confined to the Arctic. This is happening globally, really, and especially in the Southern Ocean. So we have the age of the dust here and its contribution in these colors to the total IMP concentration throughout the months. So the Arctic, we saw that the summer months, it really stood out that it was these older dusts having a contribution to the IMP concentration and actually dominating. So these crosses just show when it's over 50% is so dominating the IMP concentration. When you move to the Southern Ocean, it's even more sensitive to these older dust particles. So to summarize this, these long-lived dusts represent a small mass, but they seem to provide a disproportionately large number of dust IMPs in these high latitude regions. And they seem to provide an important supply of IMPs to the remote regions. And the reason this occurs is because these dusts eventually have a low mass but high number concentration. In terms of kind of the underlying messages, I think this does reframe how we think of dust influencing these remote regions. These are very small particles that don't have much mass. And so even though the mass is very important for a lot of different processes of dust deposition in these regions, in terms of the IMP concentration and availability, these small particles are really important, I think, and are very difficult for us to measure. So, I think the next step is to really try and support this with additional observations and see if this is consistent. So thanks very much for listening. I'm happy to take questions.
Thank you for this extremely interesting talk and findings. So do we have any questions here in the room? There is one. Can you take the green box, please? There is one here in the room.
Yes, I was thinking with the modeling, there seemed to be no clear pattern on which month had more dust recognition. One of the first slides you have, like in May, April, there was a spike of even further back with the model. One more back, I think. No, okay. I just didn't understand like why the what do you call it? the spikes are different in the model, like when it's high and when it's low, if that makes sense.
Yeah. So this slide here is showing kind of annual mean for the Arctic. A lot of these spikes and when we get these different contributions are just purely from when dust was emitted from these low latitude regions. So we know that in March, April, this is when the subtropical, like Saharan deserts are producing a lot of dust. That's when they're peaking. And so then, there's a small lag, but this is kind of being shown in this peak here. So that's why we have this sort of strong variability throughout the year, if that's the kind of thing you're asking.
Yeah, I think so. Thank you.
So there is one more question here.
Do we have, thank you for your presentation. Do you have any volume concentration results other than the mass concentration that you reported your results on? Just, I'm thinking if we can kind of compare those results with optical depths and then have kind of optical depth maps for comparing to your results?
Yeah, but I think the issue is because we're talking about it's a very small amount of the mass. If you think about, look at this picture here, the difference between the masses, 90% of the mass is only 30% of the number. And I think that kind of the weighting towards the smaller masses will also be in some way mirrored by the aerosol optical depths. I think we'll miss these really small, I don't think we'll get enough information. I think we can get some of it because I know it'll be sensitive to the size of the dust particles. And it could be, if there's a strong seasonal cycle like we see here in June, July, August, maybe that is a good way to look at it. And I think, yeah, that is a good idea, but I'm not so sure. I think we're going to need more, it's going to have to be more like size distribution observations that I know exist, and these are kind of next step to look at. But yeah, thanks for the question.
Thank you. We have to move forward, and yeah, really looking forward when you have it published, hopefully this year. Thank you. And the last speaker of this session is Erin Rai, and we are really actually happy to receive also abstracts which are talking about the Arctic haze, because it's not really often in the high latitude dust workshop. So the floor is yours. Thank you.
Well, that seems to be working.
Yes, perfect.
Brilliant, thanks. Yeah, sorry if I end up coughing through this. Got a bit of a cold at the moment. Yeah, so thanks for having me. And I'm talking about these ice-nucleated particles in these like really beautiful cloud systems that you can see on the left here that are called cold air outbreaks, and how the ice-nucleating particles in them we think are dust that is associated with Arctic haze. And so these cold air outbreaks, they occur when a cold air mass is ejected from one of the poles and it moves towards the equator. And this is an example, obviously, over the Arctic. And you can see this like lovely stratus cloud deck moving in, forming as you come across over the sea ice edge. And then you get these beautiful stratus-cumulus cloud streets that eventually break up into cumulus clouds. And we're interested in these and these types of clouds because, and eventually in dust, and we'll come to that in a bit, because of their sensitivity to ice-nucleating particles. So if you have more ice-nucleating particles in these clouds, you're going to get more freezing. You're going to get cloud adjustments where the ice will grow at the expense of liquid water, and you're going to have reduced cloud albedo, precipitation, and cloud lifetime. And all of this contributes to eventually reduce the reflection of shortwave radiation by these cloud systems. Now, that becomes important for the climate through what's known as the cloud phase feedback. So if we consider two of these cloud systems where one has very few IMP and one has lots of IMP, then conceptually we can imagine that the one with many IMP has a lot very efficient freezing and lets a lot more radiation through. Now, if we warm the climate up, then we are going to melt some of this ice and make some of these IMP inactive. And that's going to make our clouds generally brighter. But you can see there's been a much larger change in the high IMP case than in the low IMP case. So if we consider how these clouds are going to change in a warming climate, there's going to be a real feedback effect as the climate warms as to how, and these are going to cap that. The problem is that we don't really know how many IMP there are in these to begin with, and where they're coming from. And so to understand that better, we measured IMPs over the Norwegian and Barents Sea in the Arctic cold air outbreak flight campaign. I promise we'll get dust in a bit, but the point, what we're doing here, we've made IMP measurements in these cold air outbreak clouds across 8 different cases of them. And we were able to make 23 different measurements, airborne measurements over the ocean, sea ice, above, below, and upstream of these cloud systems. We derived IMP concentrations using what's known as a drop-on technique, where droplets are pipetted onto an aerosol filter sample and cooled down to see the rate of freezing. And we made online aerosol size measurements using underwing probes on the aircraft ranging from about 0.1 microns to 20 microns. Now, what do we measure? Well, we were quite surprised, actually, when we were expecting to see ice nucleated particle concentrations. I say consistent with the Arctic. There's a huge range. If you look at this graph here of many previous measurements, it's not exhaustive of ice nucleated particles in the ice nucleated particles concentrations from field campaigns in the Arctic. There's a large range in IMP concentration here, but our one sat right at the top of that, which we weren't necessarily expecting. And so that raised the question of, well, why and where are these coming from? So that led us to ask that question. We had three hypotheses. So the first and seemingly most obvious, based on a lot of literature that existed, was that it would be sea spray aerosol that was dominating the IMP concentrations in around these cloud systems. And so that was one solution. Another one was perhaps that it was terrestrial sources from the high Arctic. So we know, as we've heard many times, there is dust in the Arctic, and there's also biological material. And finally, IMPs in the Arctic haze was a potential other more rogue suggestion, which this title is sort of a spoiler here, but IMPs that may have come from long-range transport. So we had to do some detective work to try and work out which of those were. And the first line of our evidence was using what's known as the active site density of IMPs. So this is a measure based of the ability of an ice nucleated particle to nucleate ice, and its number of ice nucleation sites that it has per unit surface area. And our measurements are here in pink, and they're in line with the sort of activities that you would expect from dusts, which, bearing in mind that, you know, if you're over the Norwegian Sea, you're probably not thinking there's lots of dust. That came as a bit of a surprise. And our measurements were significantly more than would be expected for sea spray, which is the blue line here, suggesting that sea spray wasn't a dominant ice nucleator and we should be looking more at the dusts. And we gained more evidence of that from some scanning electron microscopy that we performed on a couple of our filter samples, that found that dusts, which are marked in the orange in these graphs, where you see the proportion of the number of particles that's measured on these filters, the dusts dominated the supermicron aerosol concentrations. So there was also some evidence of carbonaceous material in the submicron range. What was interesting was this was even the case in the filter that we took below cloud over the marginal sea ice and ocean, which suggests that actually sea spray is really not dominant. To account for the amount, how active the IMP were that we saw before, these graphs would need to be pretty much all blue. So yeah, the dust is really important. And there's just a note because there's carbonation material listed here. We can't distinguish with our experiment qualitatively between elemental and biological carbon, but just observationally on looking at the filters, we didn't see any obvious large biological particles. That's not to say they weren't there. So having looked at that, we then compared IMP samples that were taken and with respect to their locations relative to the cloud decks that we saw. So we looked at those above, below, and upstream of the cloud decks. And you can see that if we just look at the IMP concentration, they're relatively clustered. But once you pull this out to be as activity instead, you see the activity above the clouds is greater than those below, which means that we must be having some, which means that these dusts are the more dominantly active IMP are appearing above the cloud systems in a region where there's not much vertical, in a point where there's not much vertical transport. And this effect is really highlighted if I take the IMP concentration at minus 15 degrees. You can see that while there's a small shift in IMP concentrations, there's a five-fold shift in IMP activities. So putting these together, we think that there's a lack of surface source, particularly a sea spray source, that suggests a larger, well-mixed reservoir of vertically distributed IMP with a dust-based source. And that was then backed up by our some backstretchy work, which found that most of the samples, we found that the air masses that fed into them were floating around the high Arctic, over the high Arctic for a few days, and eventually going off to the to Europe or Canada after about a week, but generally quite high up, not necessarily interacting with the surface. And so that led us to go back to our detective work at the beginning and what our 3 potential sources. And so I think we've pretty much ruled out sea spray aerosol. The active site density that we saw was too great, and our highest IMP activities were above the cloud. So they're unlikely to get up there. So our next thing was, okay, well, what about in the high Arctic with terrestrial sources? Is there dust up there? And there is some dust, as we've heard, potentially from Svalbard, but there is, in the literature, it seems like, and people might want to come and correct me in the comments, but it seemed like at this time of year in March, there wasn't the magnitude of local aerosol emissions that we would need maybe to account for the ice aggregating activity that we were seeing. And the back trajectory analysis showed no relationship between IMP concentration and sort of surface level passes over local regions. So that then suggested that terrestrial sources in the high Arctic weren't so important. And so that only left IMPs that must have come from somewhere further off. So this dust, and Ross has mentioned that dust, a lot of the Arctic dust load is from lower latitudes. This dust that has come in from far off and has, and evidence for this was that we saw lots of it on the scaling electron microscopy, and our active site densities, again, they're in line with these. Just note that the meteorology on these days prevented any direct transport from, say, the Scandinavian peninsula. It's not to say, so that route may be ruled out. So what are we doing with this? So our current work is to look at a particular case study. There's a couple of really interesting ones, a couple of really interesting cases where we appeared to see processing and removal of IMP as these cloud systems progressed. So this is a case where we made 4 IMP measurements, 2 that were above and 2 above and below the cloud, but 1 upstream and 1 downstream in the outbreak. And the 3 concentrations of the 2 upstream ones and the above the cumulus one are very, very similar in IMP concentration. There's a real drop off by a factor of 5 below cloud downstream. And we think this might be indicative of removal of IMP and thus dust. So what we're doing at the moment, and I hope, and I'm not getting results to show you on this, and you'll be grateful for that given the time. We're doing some regional modeling. So, we're using a 2-moment microphysics scheme and aerosol measurements that we made. What we want to do is test whether the IMP concentrations that we saw downstream in the outbreaks can be reproduced given the IMP concentration upstream. We want to measure the rate at which IMP and indeed dust is removed and the dominant processes in this removal, and hopefully understand then the influence of dust that's being entrained into these cloud systems from maybe above the cloud system relative to dust that's entering the outbreaks from the north. So thanks very much. I'll leave this summary slide up, and any questions you have, we're very happy to hear.
Thank you very much for this absolutely breakthrough talk. So basically you are showing that what we have heard all the time about the Arctic haze, that the sources are only anthropogenic, that it might be also something else, and not that the whole warming of the Arctic is only related to the black carbon itself when it comes to the deposition. So, or of course the other processes like ice nucleation. So it's absolutely incredible. We had the talk about this on the lunch. I sincerely apologize. We are so late in our program, but I still believe there is time for one question if somebody wants to ask here or online. But I understand the schedule is late, so thank you very much. There is no question. Okay, one question here in the.
No question.
Yeah, there is one here.
Yes. What do you mean by the dust in the Arctic haze? You mean the coarse mode particles mixed with fine mode particles, or?
Yeah, sorry. So I should probably be a bit clear on this. So I think we, as Pavel said, like we often associate Arctic haze more with black carbon or anthropogenic aerosols, but there's actually quite a few papers, particularly from the 70s, that talk about the same transport mechanisms taking dust from, say, Asia and from the Americas into the high Arctic, like the very high Arctic. So yeah, I think is exactly what I'm suggesting. What you're saying there.
Okay, thank you.
So there is a second question here. If you can pass the microphone to Alexander. Okay, thank you. And that will be the last one I have to
Thank you.
thank you.
Really great study and very, very important for understanding the mechanisms for Arctic haze. My question is actually for this picture, what we see on the screen. You nicely demonstrate boundary layer height, but if we are going to the Arctic, the boundary layer height could be less than 10 meters.
Yeah.
And how accuracy of your study meeting such very stable boundary layers situation, and especially for transport of local sources and ice nucleation. This very sensitive mechanism.
Yeah, it's a good question. So I think that I think I'm understanding what you're saying is maybe how is that you're asking whether the below cloud measurements were representative of boundary layer measurements upstream. Is that what you meant by that, or have I completely misinterpreted?
In particular, yes.
Okay, so I think I think that there's going to be mixing over the Arctic, right? So it's being we're seeing that it's being spat out into perhaps being spat out into the outbreaks. I think it's a good point. There is a very low boundary layer at times in the Arctic. It's probably something we need to look at in more detail.
Yeah, thank you. I just stress what this is one of the problems what we need further develop and increase in our models. Thank you.
Okay, thank you, Erin, very much for this really nice talk. And I would like to also thank all the speakers of this session. Because as you have noticed, we are a little bit late. We should have started already the after break session. So let's postpone it by 10 minutes and we meet here at 2:15 or 2:10. 2:15, I guess. So it's more. So it will be slightly postponed. Each talk is one talk after. Thank you.